Hello, hello. I am Grigore Rosu, the CEO and founder of Pi². And our mission at Pi² is to bring the next million developers to Web3. We have a big problem in Web3. A critical pain point is fragmentation. Hundreds of billions of dollars are split across different ecosystems, different blockchains, different applications that try to steal each other's users instead of smoothly working together. And user experience is at best very complex. It's a process to move funds from one ecosystem to another. Our proposal to this fragmentation problem is, in one word, universality. Universality with respect to programming languages and program execution. We want all programming languages to be available to Web3 developers. Universality with respect to verifiability and different proof mechanisms. We want all of them to be used. And universality with respect to distributed consensus to assure security guarantees. We want that to be as fast as possible. Sorry, something happened here. Oops. Don't touch anything. Okay, sorry, something is going on here. Let's go back and... All right, you see, universality, one button only, which doesn't work. Okay. Our stack contains three major components. One, the universal language machine. Think of it as a blockchain in which you can write smart contracts in any programming languages. Even in programming languages that have not been invented yet, you can bring your own language, BYOL. The second component is the universal settlement layer, which allows us to generate proofs of execution and settle them across, on a common layer across various ecosystems. And that will be instant finality, instant settlement. And what counts as a proof can be both mathematical proofs and zero-knowledge proofs. You'll see that mathematical proofs are just as important or even more important than the zero-knowledge proofs. And finally, the Universal Consensus Protocol, which allows extremely scalable parallel consensus, which is not based on a total order of transactions or blocks, as in the blockchain. We'll talk more about that as well. What does this really mean? It means that we can bring, ULM means that we can bring all developers in all programming languages to Web3. Any developer is a Web3 developer. USL means that we can now prove correct execution across any applications in blockchain or not, in Web3 or Web2. That includes millions of applications around there. Everything, everybody who wants to prove that something happened can settle that computation on the USL. And UCP means that we can have consensus at optimal speed. You cannot do any faster than that. Again, same problem. The market opportunity for this universality that Pi² brings is immense. The world of developers grows from 20, 30,000 of developers as we have today in Web3 to 30 million or even 100 million if you include all the AI prompt developers as well. Essentially, every program in every programming language can now become a Web3 program. a few words about universality. So why we want universality. But before diving into why we want universality, let's first try to understand why we don't have it already. What stays in the way? Programming language barriers. Programming languages are not easy to implement and to integrate in an ecosystem. Because for each programming language, you have a variety of tools that you want to offer to the developers. And you have cross-product between languages and tools. And each of these arrows is an entire complex system by itself. For example, compilers for C took 40 years to develop them, or interpreters for EVM. All these need to be implemented in order to be deployed on blockchains, which is a highly, highly non-trivial task. And not to mention maintenance, which is a hell. You have to maintain all these tools as languages evolve. And all languages evolve. All languages worth their salt evolve. We have a new version every few months. What is our secret sauce? The secret sauce, what brings us universality, is the K framework. The K framework was invented 20-ish years ago when I was still a researcher at NASA, and I moved to academia. And what K offers is this complete separation of concerns between programming languages and tools for programming languages. You define a programming language, or implement a programming language if you want, once and for all. And once you have that, which is a mathematical theory, now the K framework generates any tool that you need for your language. But what is really important here is the fact that K is a prover, mathematical prover. So everything that these tools will do to the right is supported by a mathematical proof under the hood that K constructs as it performs that task. For example, for execution, when you generate an interpreter for EVM, let's follow this path, the interpreter will not only execute EVM programs, but will also generate a mathematical proof why the execution of that EVM program is correct. And that allows us to separate concerns, which is a golden principle, programming languages from tools, while at the same time assuring correctness by construction. We call it correctness by construction. Very quickly, to give you a flavor of what it means to define a language in K. This is a complete definition of a simple language, which has only 39 lines. Here you have the syntax of the language. Here you have the semantics of the language. In the syntax of the language, you have usual context-free grammars describing how statements look like if then else, which is strict in the first argument. That means that we have to evaluate the first argument. On the right, we have semantics, and what's important here is you have like one semantic rule, which is an axiom, mathematically speaking, for each language construct. For if then else, well, it depends on how many cases. If then else has 2 cases, so it has 2 rules here. What is important here is not the details, but the fact that this is all you need to do in order to plug and play a new programming language. You define the language like this, and now plug it in K, and K will give you an interpreter that also constructs proofs under the hood. We are going to demonstrate this language, actually, a slightly more complex version of this language shortly. So pi squared comes from proof of proof. The name pi squared comes from proof of proof, specifically from zero-knowledge proof of mathematical proof. Why? Because K already gives us mathematical proofs, and now we generate ZK proofs from mathematical proofs. Bear with me for a second. All right. So at a very high level, this is how it works. You start with a program and an execution environment, same like in any ZK VM or VM for that matter. And what we get at the end is a zero-knowledge proof, same like in a ZK VM. What is different and critically important is the fact the programming language itself is an input. And also what is super important is that after K does its magic, we obtain a mathematical proof here that stands for the correctness of the execution of the program on that input, in that execution environment. Now, all is left to do now is to verify the integrity, the correctness of this mathematical proof. And we can use it, we can do it using any existing ZK technology or new ZK technologies. What I insist to observe on this slide is that one circuit works with all programming languages. You don't need one ZK VM for each VM, for each programming language. You only need one circuit for mathematics, and now you got ZK VMs for all languages and all VMs. That's why we call this verifiable computing, this picture, verifiable computing 2.0, because it is verifiable computing as you know it, but it is universal and correct by construction. Universal because it works with all programming languages, and correct by construction because there is nothing to formally verify. ZK VMs need to be formally verified, which is a very complex process. Here you don't have to verify anything specific to any particular programming language. Moreover, the ZK circuit can be implemented using any ZK VM. So you can bring universality to any ZK VM this way, following this path. All right, so that's the theory. Now, what's the current status? 1 year ago, when we started the company, Pi Squared, actually exactly 1 year at the previous ETHDenver, this was our wish list. The K framework, in spite of being correct by construction, generating mathematical proofs, was slower, not in spite, it's kind of expected it was slower than handwritten interpreters, in particular, about 10x or 1,000% slower than Get. That was a big challenge. We had to improve the performance of K. And I'm happy to say that now, with all the optimizations that you can do at the mathematical level, mathematical proof optimizations, proof engineering, we managed to execute EVM programs actually faster than EVM. All right, this is, again, very important because it's not only that you get a correct by construction execution that builds a mathematical proof under the hood, but it is also faster than the ad hoc manually written interpreters. So performance is not an issue. Whoever tells you that formal semantics is great but it's slow, tell them no, not anymore, and send them to our white papers. All of these optimizations and techniques I explain in detail in the white papers. The second task that we really wanted to get accomplished very quickly was to prove the concept, to prove the proof of proof makes sense, that it makes sense to generate a mathematical proof and then a zero-knowledge proof out of it. And initially, we wanted to use just one ZK VM, which was risk zero. But very shortly, we started talking to different ZK VM developers, and everybody was interested. And before we knew it, we had 7 different implementations of our ZK circuit using all the major ZK VMs. And also, we have a benchmark now that contains more than 1,200 tests, multiplied that by 7. And many people think that this is actually the most extensive benchmark ever developed for ZK VMs. It's all public, everything is open source. You can also read the white paper to see the details and how the whole thing works. Finally, we wanted to demonstrate that we can generate mathematically provably correct claims from Ethereum transactions, Ethereum blocks. So more or less to mirror Ethereum on the USL by proving every single block mathematically. Nobody has done that before, by the way. We heard of zero-knowledge proofs of blocks, but now mathematical proofs of blocks, okay, more rigorous than that. Well, we've done more than we expected. Actually, we'll see a demo today by my colleagues here, that not only that we've done that, but we also integrated USL with Wormhole. And now we can use USL instead of Guardians to prove all the transactions and to have instant finality. And also with the pod protocol that gives us maximum, optimal consensus. And our pod colleagues are also here. Thank you. Finally, one thing that we didn't plan initially, and now it's done and we'll demonstrate it as well, was to actually demonstrate an Ethereum-like blockchain that would support all programming languages. Right? That's what we want, after all, to plug and play our language. And what would be easier to understand than an Ethereum-like blockchain where you can do certain transactions and plug a new programming language and then write smart contracts in that language. It turned out that that was a lot simpler than we imagined to do. Sometimes when you do things, the right things right, they are simpler than you expect. So we are going to demonstrate that as well. So it's basically a blockchain ULM that supports all programming languages. And moreover, it is implemented using for consensus on top of the pod protocol. And with this, I will pass it to Ovidiu, who will talk about this blockchain ULM and will demonstrate it as well live.
Thank you, Grigore. GM, everyone. My name is Ovidiu, and I'm glad to talk to you about ULM, which is something I've been working at with PySquared for the last few months. And we're very proud of what we achieved up until now. In the sense that you will see that in just a few minutes, we will be able to have one blockchain where you not just bring your own language, you bring your own languages. For now, we support Solidity, EVM, WASM, Rust, and also a special language that you've probably never heard about up until now, but you will. And we'll soon have also Move, Python, Go, JS, and so on. Now, let's talk some theory first. I'll be brief, I won't bore you, I promise. So, when it comes to formal semantics, it's basically a mathematical definition of all behaviors of all programs in that language. Meaning that if we have that mathematical definition of said programming languages, we can know how that programming language behaves in any VM, ISA, computational model, and so on. Moreover, we can have, using that definition, automatically generated language interpreters that are correct by construction and fast. Now, how do we get this and put it on a blockchain? We do this by having interpreters that should be able to modify the same blockchain state. That's one precondition. And we solve that by having all semantics implement the ULM interface. And second of all, we have smart contracts that need to interact with each other. I want to have my EVM contract calling your WASM contract without any issue. So that's why we have contract calls that take place through ABI encodings, meaning that all smart contract interactions are programming language agnostic. Meaning that if I have an EVM contract, I don't care that your contract is WASM, I can just call it like any other contract, and we'll prove that soon. Now, let's see how everything works for a minute. So first of all, we have a transaction that goes into the ULM, and that transaction is a contract call. That contract call sees what semantics it has to use in order to execute said call. Maybe it's EVM, maybe it's Rust, maybe it's Move, and so on. And using a ULM interface, reads and writes to the blockchain database. And that's how we do all those changes. The ULM interface basically abstractizes everything that's programming language specific when it comes to interaction with the blockchain database. And that's the beauty of it. Now, we went through enough talk. Let's see something hands-on. So with that being said, Musab, let's go through the bring your own language demo. So this is our quick demo. in which we show you how to bring your own language, meaning that you can just come to the chain and in the same way you would have a smart contract deployed, you can deploy your own language, which will work and can then be referenced in smart contracts to use them. And let's see how we're going to do that. And you can see in the top corner that we have a language registry, which shows all the available languages that we have on chain. For now, we have EVM, and that's relevant, obviously, because it's the basic programming language for EVM-compatible blockchains. And it's K beforehand, and it's important because it's not the usual execution engine, it's rather implemented in K, and that's how we run programs, by using K, not by having the usual execution engine. We also have the ID, which I'm going to show why it's relevant later, and the hash, which helps prove that the language that we're running is authentic. Basically, by having the ID and hash of a programming language, we can check that the programming language that we're using in a smart contract is the language we expect it to be. We can also, using that hash, check in the node, as I said, and we have this definition here as well to see what you see here is the definition of said programming language. We won't lose too much time on this. It's just interesting to see all the complexity behind it, but on-chain, we don't care too much about the specifics of it. Now that we have the hash, what we'll shortly do is add one more language. And as we add a language, we see that we can choose any language that we want, and we will quickly add Solidity. As you see, we have the definition here, and as this definition will be added on-chain via a transaction. You can see it's a transaction like any other sent via MetaMask. And we also have a disclaimer showing what we have saved on-chain, URL, language ID, definition, and so on. Now, the language is there. We can use it. It was that simple. And attention, this is Solidity. We're not compiling it to EVM. We take the ID and input the ID here, because we use it when deploying a contract to tell the node, hey, this contract will be in this programming language. It's relevant. That's the code you need to run. And as we do that, let's deploy a token that is directly Solidity on-chain. Now, we're deploying a USDC copy. You can see the Solidity code there. And attention, we're just hex encoding it and sending it to the blockchain. You can even see that it's recognized as a contract deployment transaction, without doing any change to MetaMask, of course. Now, as this transaction gets completed, we have the address of said contract that we can simply copy and then use to interact with the contract. Now, we input the address, and as the address goes on, we also obviously need the ABI, because that's the usual interaction that we use for all contract interactions. And we will use the USDC API. We have some options there because we're in a demo mode. Now, we load said contract, and we can see USD coin, symbol USDC. We quickly copy our address, check our balance. Obviously, our balance is 0 because we just deployed a contract. And we're going to mint some tokens. We're going to mint pi squared tokens, 986. And you can see it's a simple transaction like any other. Now, we don't care anymore that the contract is directly in Solidity. All we care about is the fact that it's a contract and we can interact with it. And we have the transaction receipt, which shows that it's working like any EVM execution engine. It's, again, language agnostic. It doesn't care that it's written in Solidity. And now, as I read my balance, you can see that I have 986 tokens, which is amazing. We have interacted with a Solidity contract directly, and we're going to show that on-chain as well. Now, you can see that it is detected as being a Solidity contract, and that's relevant. How does the Explorer know this, even though all contract interactions are language agnostic? Well, we'll show you exactly. If we see the contract code, you can see it's hex encoding, but the first 4 bytes are the ID of the programming language used. That's the only change we make outside to the EVM interface to say so. We have the language ID, which is basically how the node knows, okay, I will run this code using this programming language. Now that we have done it, let's add one more language. Now, in order to go a bit faster, we will use the predefined menu, and we will deploy Rust. You see, it's just as before, nothing special when compared to Solidity, but very special in general. Special enough in the sense that with a simple transaction, we enable 3 million Rust developers to use our blockchain, and we use the language ID, we deploy a contract, we're deploying a wrapped Bitcoin contract, and as this contract goes on, we're pretty much going to go through a similar flow as we did with Solidity. And as we do it, you can see wrapped Bitcoin as the name, you can see WBTC as the symbol, but now we will use the allowance endpoint to show that it works as well. Now, as we use this endpoint, now we will use just pi as our mock value. We send the transaction, you see it's recognized as a spending cap request. MetaMask has no idea this is Rust, and MetaMask shouldn't even know it is Rust. This just makes it greater. Okay, the transaction is completed and we have this on chain. We have the spending cap increased, and we can also see it on chain. You can also see that once again is detected as a Rust contract. The language is known because of the ID here. The code is again hex encoded, but is directly Rust. And you can see we have the free languages. And now what we will do is also run some KVM code to show that it works as well. So you saw before Solidity, which was directly Solidity. We didn't compile it to EVM. Now let's see some ugly EVM bytecode being executed. Now we put it on chain. This is wrapped Ethereum, and as opposed to other tokens, we will need to deposit Ethereum to actually get wrapped Ethereum back. So you can see the name there, wrapped Ethereum, and what we'll do is we'll check our balance, which is 0, and we will deposit some Ethereum. We will deposit 0.1 Ethereum, and we confirm the transaction. We see that all works well. We wait for the transaction to be completed, and as the transaction is done, we have the receipt again, all well. The balance is here, 0.1, and we can also see the balance here. The contract has received 0.1 Ethereum from us without any issue, and it's also depleted from my own balance. And we can also check it on the Explorer. We can see that it's recognized as a KEVM contract, which is the usual EVM. We can see it has 0.1 Ethereum. Basically, it works without having to worry about anything that is programming language dependent. Users don't even have to know it's written in something specific. Now we add WASM quick as well. The transaction is going to be completed any second now. And boom, we're now at our 4th language in just a few minutes. We also deploy Doge in WASM. And as the transaction gets deployed, we will have the address, and we'll once again look to mint some tokens in order to show that it works. Okay, you see Dogecoin, Doge, all's good. We copy the address, we see our balance, we go and mint, yada yada. Here goes the transaction, and now we have the balance there. Good. So we had Rust directly, and we also had Rust that was compiled to WASM. And yeah, it's as easy as that to say that. Now, we have shown some impressive languages, some very well-known languages, but you don't have to use something that's already created. You can just create your own programming language, which is simple in this case. We created a programming language just to test things around and see that it worked. Why we did that? Well, because we can, and we want to show that you can create your own programming language as well. It might be good, it might be bad, but the point is it's going to be supported on chain without any issues. Now, as we have deployed Simple, we are going to also deploy a contract in Simple. And because it's our own programming language, we're going to deploy our own mock Pi2 token. Now, we go real quick to deploy it. And as we confirm it, we will get the address and once again go through the whole process. And if you are thinking, oh, he's at the third token already, how many more is he going to mint? If you feel like it might be a bit boring, great. It should be. Having multiple programming languages shouldn't be exciting or complicated. It should just be there like a normality. Now we mint 9.86 tokens, Pi2. And as the transaction gets completed, we check the balance and it's there, obviously. We also check it on chain. We can see we have the Pi2 token that is detected as being in a simple programming language. The language ID is there, easy to see. Now, what we have just done is have 5 different programming languages on the same blockchain in under 15 minutes, for sure. This is amazing. And it's not just that. We have more. Musab, I think you can stop this, and we can go back. We can go to the next demo, which is going to be the decentralized exchange demo. We're going to show how you can basically have a DEX that has multiple programming languages interacting between them. Basically, you can have a token that is created in one language and swap it for a token in another language. Now, let me explain the setup real quick. So we have our DEX contract, the router, the Pi2 token, the Web Bitcoin token, DAI, USDC, and Doge. You can see real quick, our router, that is the DEX itself, is an EVM contract. Next, you can see the ID there as well, as it's EVM. And next token is Pi2. You can see it's in Simple. Next token is Web Bitcoin in Rust. Next is DAI, it's EVM again. Next is USDC in Solidity. Next is Dogecoin in WASM. And what we're going to do is do a quick swap. We'll swap from USDC to Doge. What's relevant to know here is that here we don't show the programming languages because the interface does not care about the languages. You can see it's recognized as a spending cap request first. You have to approve the spending of tokens for the contract. And here it goes. Once the spending cap is processed, we will have also the transfer request. We approve that as well. And as that gets done, you are able to see that our balances have changed. And we can also check that on-chain. Now, this is my favorite part. If we look at the transaction on-chain, you can see that we have interacted with a KEVM contract, transferred 986 Solidity tokens, and received back 895 something Doge tokens that are in WASM. 3 programming languages interacting between each others in one single transaction or contract call. That is as amazing as it gets and as simple as it gets. It's not, I wouldn't even call it language agnostic. Like, the DEX, not just that it doesn't care about the language. The DEX doesn't even know they exist. It's language atheistic, if you want to call it like that. And you can see that it works as we say it does, in the sense that here's the code of the DEX, and here's the transfer. No programming language is specified. You can see that it's just where we send, what we send, and so on. And this is because we use, as we said, ABI encoding to basically make sure that all the inputs and outputs that are sent between programming languages are, let's say, normalized. So again, KVM, Solidity, WASM, one transaction working together without any issue. So this has been our multi-language swap demo. I think you can stop the recording, Musab, thank you. And that being said, I want to give the mic to E to continue with our next cool products.
Hello, everyone. My name is E, and I'm glad to be here. So first, I'd like to thank Ovidiu for his very informative presentation on these universal language machines. So next, I will talk about our second component in our universality stack, which is the universal settlement layer, and we call it USL. So if I want to give one sentence to describe what USL is, then it will be bring any off-chain data to on-chain in a verifiable way. So there are two keywords in this sentence, the data and verifiable. And this corresponds to two important concepts in the USL, which are claims and proofs. Claims are anything provable, and the proofs are something that used to verify the correctness of the claims. So let me try to give you some examples of different claims and proofs. So first, we can use claims to capture the computations in any program languages and VMs. For example, we can use block transition claim that is interpreted as this tuple, the pre-state, the code you can think of as a list of transactions, and the post-state. So this tuple can capture the blockchain transition in any rollups. And we also can have this blockchain query claim that simply we call this view function on a certain state to get some results. And these claims can be verified through different mechanisms. They can either be verified through mathematical proofs, or they can be verified through CK proofs in any approved CK VMs. And even they can also be verified through re-execution. Then we can also have the consensus proof, which basically states that a claim is included in a canonical blockchain. So the accompanying proof is usually a list of signatures from all the validators that approve this block. And we can also use the claims to capture those vetted knowledge or information like oracles or identity, and we can prove them through digital signatures or certificates from zkTLS. So now we have some basic concepts of claims and proofs. The USL is just a decentralized network of incentivized verifiers. And those verifiers receives claims and proofs from users or applications and verifies them. So there's one important property of USL that I want to highlight. First, we require those claims to be self-contained, meaning that they can be verified independently. And then all the verified claims actually form a set instead of list or sequence. This is very important because the order of the verification is not relevant anymore, and actually they can be verified in parallel. This important property can enable us to achieve fast finality if we choose the underlying consensus protocol properly. That I will talk about it more in the implementation slide. So once the claims are validated, and then the claims are accumulated in this validated claim set, which is the state of the USL. And the USL also provides this so-called membership or inclusion proof for user to check whether a claim belongs to the USL state. So, and this membership proof are succinct and can be checked very efficiently. And all the applications or blockchains who wants to connect to the USL only needs to implement these simple verify membership functions. Okay, now so far I covered this universality of USL, which it incorporates various types of claims and proofs. And also, once the claims is verified on USL, it can be used everywhere. Next, I want to talk about this our implementation of the USL settlement layer. And we are collaborating with the pod team. Actually, we're implementing the USL on top of the pod. So first, what is pod? The pod is a layer 1 primitives that receives transactions as input and produce logs as output. But unlike the traditional blockchain or consensus protocol, so the pod doesn't provide a persistent total order on the transactions. In fact, the order of transactions are subject to change over time. And by accepting these features, it actually allows for making very performant systems. And the pod team has produced some theoretical results showing that pod is optimal in latency and throughput under some constraints. So as we said, we implement our universal settlement layer on top of pod. We implement the verification logic as a precompiled and deployed as some specific address on top of in the pod network. And submitting claims and proofs to the USL is equivalent to send this verified transaction to the pod network. So once this verified transaction is executed successfully, and it will be appended to the pod log. And we have this USL client to query the pod network for this log and the membership proof. This membership proof is just an aggregation of signatures of the validators from pod who approves these transactions. And then we can use these claims and membership proof anywhere in those dApps. So next part, I would like to introduce real use cases of our USL, where we use USL as a verification layer for the wormholes entity framework. So the wormhole entity framework is a native token transfer framework that allows users to transfer tokens between chains by burning or locking tokens on the source chain and minting tokens on the destination chain. So under the hood, there's a message verification layer which verifies the messages between chains. And it also allows developers to introduce their own message verification layer, and they can configure which message verification protocol to use at runtime. So this is basically the basic workflow and how we use this USL as a customized message verification layer. So first, user submit bridge transactions to interact with the entity manager. And this entity manager contract will burn the tokens on the source chain and construct an entity message that specifies the amount of token to be minted on the destination chain. So the message will be stored on the source chain, and we have this claim generator off-chain component to monitor the transactions on the source chain, especially those bridge transactions, and generate claims and proofs, which we will see in a second, and submit those claims and proofs to the USL. Once these proofs, claims are verified on the USL, the relayer component will query the USL for the validated claim and the membership proof and submit it to the destination chain. On the destination chain, it will first check the membership proof by running this verified membership function, and then they will parse the validated claim to extract useful information and performs the token minting. Now let's go to see the real demo. So I have prepared 2 demos, and let's play the first one. Okay, so this is the bridge demo where it allows user to transfer tokens from Sepolier to Arbitrum Sepolier network. So in this transfer tab, it is a very basic bridge interface. And on the upper right, there's a FOSI button to allow user to mint some test tokens. In the history tab, it basically shows the bridge transaction histories, and each entry contains information like the source and destination transaction hashes, the pod transaction that verifies the claim and proof, and the claim itself. Now let's move back to the transfer tab and transfer some tokens. We already approved a limited amount of tokens, and now let's input some token to transfer. So okay, let's input 11 and then click the transfer button. So the standard is quite, the workflow is quite standard, and we approve the bridge transactions on the source chain. So now let's go to the history page and wait for the bridge transaction to be completed. As you can see, now the transaction on source chain is completed, and the pod transaction is completed, and we just need to wait a little while for the destination chain to be a transaction to be completed. Okay, now the bridge is completed, and we can click each link to verify what is happening. So we first click the link on the source chain. And we can see that the amount of token is actually burned on the source chain. And then we click the transaction on the destination chain, and we can see the same amount of token are actually minted on the destination. As we said, so actually what happens under the hood is that our claim generator generates claim about the entity message and then submits to the USL for verification. Now let's see what the claim and proofs actually look like. So we can click the claim button, and it will show you the hex format. And we can click the decode claim, and it will transform this hex format into human readable format. So in this assumption field, it shows the block header of the current block being queried. And then this action field shows the actual view function that we are called on this blockchain state. And the result is the entity manager that is being stored on the source chain. And we can further decode it to see the actual tokens, the amount of tokens to be minted on the destination chain. Now we can go to the proof tab to see the actual proofs that is being generated. They are actually the Merkle inclusion proofs for those storage keys that are being used to execute the view functions. OK, great. And then once the claims are verified on the pod, right, and then the relayer will submit this verified claim and proof to the destination chain, and we can check the transaction of the pod on this pod explorer. Finally, let's go back to the transfer page and verify that all the balances on the two chains are updated correctly. So this is the end of the first demo. OK, so let's play the second demo, where I will show you a scenario where the claim generator stops working and the user can still complete the bridge transfer in a trustless way. So let's first stop the claim generator and then performs a normal bridge transfer. So we enter 21 tokens here and do the transfer. We click approve the transactions in the MetaMask, and we go to the history tab to see what actually happens. So now the transaction, a source transaction is completed, and we can see the amount of tokens is burned on the source chain. However, since the claim generator is not working, so no one will generate claims and proofs, and the whole bridge workflow gets stuck. Instead of waiting for the developers to fix the issues, the actual users can start the claim generator locally, because the bridge is actually by the claims and proofs. It doesn't care who actually generates the claims and proofs, as long as the claims can be verified by USL. So now let's do that. Let's start the claim generator in manual mode. Once in the manual mode, user needs to provide the transaction hash of the source chain and submit it to the claim generator. Let's copy it from the Explorer and give it to our local claim generator. Now we submit it to the local generator, and boom, you can see that it is its job to generate proofs and claims and submit it to the pod, and everything goes well. Now we can check the destination chain transactions. And verifies that the actual amount of tokens are minted on the destination chain. I think that this concludes my demo. So, and I will hand over the presentation to Grigore for the UCP component.
All right, thank you. I hope you guys are as excited as we are about what happened here. Let me put things a bit back into perspective, okay? So we've seen multiple programming languages on the same blockchain. And we've seen programs written in these multiple programming languages where they interoperate on the same blockchain. Programs written in WASM, Rust, Solidity, and Simple. But Simple is a new language altogether. All of them on the same blockchain. okay? It felt and looked like any blockchain using MetaMask to do transactions and everything. But what happened under the hood is critical, because everything was turned into a mathematical proof that was checked. Okay, so everything is mathematically correct. You don't have to worry about an incorrect implementation of an interpreter or compiler, right? Because everything was executed with the actual mathematical definition of the programming language. That has never happened before. Okay, we've seen zero-knowledge proofs where you have a way to generate a zero-knowledge certificate for an actual interpreter. Here, there is no interpreter, actually. There is just a mathematical proof that justifies an execution. The interpreter only helps generate the mathematical proof. Then we've also seen how we can implement bridges, so basically programs across different blockchains and different languages, also using the same infrastructure, where claims are settled once and for all at the speed of light, using a protocol called the Universal Consensus Protocol, inspired and done in collaboration with the pod colleagues from the new pod company. We're also writing a paper together, so we cannot tell you a lot about the protocol right now. But what is important to know is that every single transaction generated a claim, which is a rigorously proved mathematical fact, which is verified by a decentralized network of verifiers who agree that that is indeed correct. And that happens only with a round trip of messages. So it's the maximum, it's the optimal possible consensus that you can get. And with that, we have a few minutes for questions before, or maybe let's put this again into perspective before you ask questions. What really happens here is that now we can use all programming languages to write Web3 applications. The programming language is not a barrier anymore. You no longer have to learn weird programming languages only to become a Web3 developer. You can use your favorite programming language. All you need is to plug and play it into the Web3 framework, and you've got it. That opens the Web3 space to millions. And if we include AI inferencers and AI prompts, hundreds of millions of users. And that's how it should be. With that, we thank you, and we are open for questions. We have 5-6 more minutes for questions in case anybody has any question. Thank you, first of all. And questions, please. We can pass the microphone for questions. We save some time for questions on purpose. There is no bad question. Please feel free to ask anything.
What's the timeline to get to production or mainnet for the tech?
Oh, good question. So 6 months, let's make it simple. 6 months for testnet, 1 year for mainnet. And mainnet for us means the USL network that can settle claims in any languages and interconnected with several layer 1s and layer 2s as well.
Hi, my name is Nico. I'm super excited about what you guys are building. And something that I wanted to ask you, maybe you already sort of explained it, but I didn't get it, so sorry in advance. For the programming languages that you can implement, how different can they be in terms of, is it only syntax that, for example, you are building something in Solidity and then you're going to be able to build it in Rust? It's like Solidity with syntax on Rust, or how deep can you go with that?
The languages don't know anything about each other. There is obviously an API, a storage API they have to agree on. So they read and write using an API. So you have, when you define the semantics, you have to accept that API and define the semantics using that API.
Yeah, and that was my question about the API. The API is sort of like a generic form of what Solidity does. So in some level, you're still going to be we'll have to take care of some bugs that are in Solidity, but in Rust, because of the way that that API is. Basically, like the question is, how deep can you go with the language, and how different they can be between them before
So
beside the syntax?
You have to stop at some moment where you say, this is my storage model, and every language has to agree on the storage model, how you access the storage model. For example, move. Move has a slightly different storage model, more general than EVMs, but they can live together. We can go, that's very technical, it gets very technical. In some sense, that is what we call semantics engineering. So when you define a language, it's an engineering process, and you have to understand the semantics, you have to understand the built-ins on which you build your semantics. Like numbers, you have to pick numbers, you know, infinite numbers, finite size numbers, and so on. And similarly, you have to build to accept your domains on top of which you define computations above. And this is a moving target, even for us now, the storage model. We keep improving the storage model as we add new languages.
Thank you so much.
Any other questions?
Or you guys want to add more on that, on the storage model? No. All right. Thank you for the questions, and thank you for being here. And I hope you'll soon try USL and ULM. You can try them right now. Go to our website, and you'll find them there. Thank you.